Yeah. Namaskar, good afternoon. Dr. Soni, we can start now. Am I audible, Dr. Soni?
Yes, sir. You are audible, sir.
So we can start now, Dr. Soni or Dr. Bogi.
Hello, sir.
We can start now.
Yes, sir. Yes, sir.
Excuse me, sir, you are not audible.
Is it audible now, sir?
Sony sir, you are not audible, sir.
Okay. Respected Dr. K. Ramesh Saab, respected Professor V.K. Dadwal Saab, distinguished participants for this popular lecture being organized today by India Meteorological Department in collaboration with National Institute of Advanced Studies to commemorate 150 years of India Meteorological Department. As all of us know that IMD was established in 1870 and it will continue, it will complete 150 years on 15 January 2025. Through this long journey of 150 years, there has been many successes, many lessons learned, and many interventions with respect to policy, planning, exhibitions. As a result, IMD has grown over the years to provide the required weather and climate support for overall development of the country, socioeconomic improvement of the society, and the individual at large. There has been manifold increase with respect to the acquisition of data, its analysis systems, development of the climate, provision of numerical modeling with supported by high performance computing system, generation of forecast and early warning, and its dissemination to various stakeholders and users. Though IMD is a nodal agency, it is supported by many national agencies, including the state governments, central governments, organizations like Indian Space Research Organizations, and many others like Indian Air Force, Indian Navy, Indian Coast Guard, Defense Forces, and many more. So therefore, this journey of 150 years is not limited to India Meteorology Department, but is journey of the meteorological fraternity. As a meteorological fraternity, we have proved ourselves as a strong force in international arena, not only to provide the innovations and discoveries in the science of meteorology, but also the applications for the betterment of the society at large, following the concept of Vasudhaiva Kutumbakam. So while we consider all these aspects, the talks which are scheduled for today demonstrates the collaborations, the collaborative research and development, which played a significant role in improvement of the service to the society, conversion of science to the societal applications. I, on behalf of India Meteorological Department, on my personal behalf, express deep gratitude to Dr. K.J. Ramesh, former Director General of Meteorology, and Professor V.K. Dodwal, currently the professor in National Institute of Advanced Studies, former Director of IRS, Director of NRSC, and Director of IIST. It is really a golden opportunity for all the participants and viewers joining through YouTube and WebEx system to listen to these two giants and learn about the evolution in the past, the current status, and the future challenges and prospects. I am sure, especially the young scientists and engineers participating in this program will be ignited with the talks by these two stalwarts. We will remember both of you, sir, for your commitment, dedication, and involvement with India Meteorological Department for betterment of service in a joint manner, and also for your leadership in various angles provided to India Meteorological Department, though directly by Dr. K. Ramesh Saab as DG, and of course, indirectly in various fora and various committees by Professor V.K. Dodwal Saab. With these few words, I welcome all the participants, delegates, organizations participating in today's webinar, and express my congratulations, compliments, and deep gratitude to Professor V.K. Dodwal and Dr. K. Ramesh. Thank you very much.
Now I would request Dr. Puyarasan to welcome today's speakers, Professor V.K. Dodwal and Dr. K.J. Ramesh, by presenting a flower bouquet. Thank you, Puvi. Both the speakers do not require introduction to this meteorological community, but still I would request Anup to formally introduce our speakers today.
Thank you very much, sir. A very good afternoon and namaskar to all of you. I'm Dr. Anup Misra from India Meteorological Department, New Delhi, and I'm delighted to get an opportunity to introduce our speakers for today's talk. We have a couple of talks by Professor V.K. Dadwal and Dr. K.J. Ramesh this afternoon. And it's an honor to have Professor V.K. Dadwal as a speaker who will be delivering a talk on role of meteorology and role of satellites.
Share
in
your
meteorology.
screen. Please share your screen.
It's shared, sir.
No.
It is not moving. Yeah.
Is it
Now,
moving,
yes.
sir?
Now it is moving. Please go ahead.
Yeah. And Professor Vinay Kumar Dadwal is currently Indira Gandhi Chair Professor of Environmental Science in School of Natural Sciences and Engineering at NIAS. And Professor Vinay Kumar Dadwal completed his PhD in plant physiology in 1983 from Indian Agriculture Research Institute, New Delhi. And he joined Indian Space Research Organization in June 1983 and was with ISRO for 38 years till his retirement in July 2021. He has headed 3 ISRO units, namely Indian Institute of Remote Sensing IIRS during 2004 to 2010 and National Remote Sensing Center NRSC during 2011 to 2016 and Indian Institute of Space Science and Technology IIST during 2016 to 2021 and joined NIAS as chair professor in August 2021. He has extensive research experience in use of Earth observation data for agriculture, land transformation, land surface processes, disaster management information support, hydrology and terrestrial carbon cycle. At NIAS, he continues his research on quantification and modeling of terrestrial carbon cycle of India. And he was project director for National Carbon Project under ISRO Geosphere Biosphere Program, a multi-institutional network, national effort that established an observational network of carbon flux and atmosphere. CO2 and atmospheric CO2 and geospatial mapping of national forest biomass and soil organic carbon in high detail. He has published more than 300 papers as author and co-author in peer-reviewed journals. As a science leader, Professor Dadwal has extensive experience in bilateral and multilateral space cooperation, including member leader of Indian delegation to the UN Committee on Peaceful Use of Outer Space from 2012 to 2016 and was chairman of 53rd session of Science and Technology subcommittee of UN COPUS in 2016. And I'm elated to introduce Dr. K.J. Ramesh, who will be delivering a talk on characterization of climate change-induced precipitation extremes. Dr. K.J. Ramesh is the former Director General of Meteorology at IMD and permanent representative of WMO during 2017 to 19. Dr. K.J. Ramesh holds a PhD in monsoon dynamics from IIT Delhi and has over 40 years of experience in field related to weather, monsoon research, hazard assessment, and climate. He is currently a senior advisor of RIMES, Asian Institute of Technology, Bangkok, Thailand. He was involved in monsoon research at IIT Delhi for 10 years, followed by being a group head at NINSEMA WF and head disaster management unit of Government of Andhra Pradesh. In Ministry of Earth Science, was heading atmospheric science services and climate change research program development. He also worked as a former member of technical committee for air quality at NCR New Delhi and adjunct professor in National Institute of Advanced Studies. He has actively led and engaged in multi-hazard mitigation framework development at Department of Science and Technology, cyclone and flood hazard mitigation for Godavari, Krishna rivers, and operations of dams and reservoirs. As head disaster management unit, Government of Andhra Pradesh, He also served as member of Indian delegation for UNFCCC negotiations on climate change that issued June 2008 to 2016. He also served as member core group's National Disaster Management Authority for development of guidelines in respect of cyclones, flood, disaster communication. He has published over 50 research papers in various journals. Kindly join me in welcoming Professor Dadwal and Dr. KJ Ramesh for this talk.
Thank you, Anup. And now I would request Professor Dadwal to kindly deliver his lecture.
Share the screen. I don't have specs. Satellite meteorology. This one, no? Yeah, this you can cancel. Yes, sir. It's started. Which one? Share.
Good afternoon. Good afternoon, Dr. Mahapatra, Dr. Soni, Dr. Anu, and Dr. KJ Ramesh. It's indeed a honor and privilege to be introduced by DGIMD and past DGIMD sitting here. What I understood was that some college students are the prime focus of today's lecture. So it is kept at a very, very preliminary level. And the whole idea is we will just see why these satellites are important, what do they do, and what are the Indian satellites. Some mention we will make of the other missions also. So we would, what I aim to do is just give you a very small background and the institution history, because it's a very momentous occasion of just 2 months short of 150 years of India Meteorology Department, right? So we must, and before we talk of various types of satellites and remote sensing, then we will talk of sensors, orbits, right? And then the major missions. Then what do they do over ocean, atmosphere, land, and geophysical parameter? And finally leading to climate change and essential climate variables. Then we will have a very short introduction of past, present, and future satellite. Past, we won't start from the very big. And then, of course, IMD uses extensively, which I will just point you to their website and shortly introduce. I hope to finish in around 45 minutes. Is that 45 minutes? Because I think that is very important. So for all the younger generation, it is very important to start at the beginning. So you must have clarity of what exactly is meteorology. So there are hundreds of definitions, each varying. I have chosen to introduce you to the American Meteorological Society definition, which says that it will be study of chemistry, physics, and dynamics of the Earth atmosphere, including the related effects at the air-Earth boundary over land and ocean, and fundamental topics of composition, structure, and motion of atmosphere. The goal ascribed to meteorology are the complete understanding and accurate prediction of the atmospheric phenomena. So, in the meteorology itself, forecasting actually is a very, very important thing. Now, what if you really, this will be here for a minute, so you can go through this definition again. So, basically, for many of these phenomena, the starting point is observation. So, observations, there were since time memorial, observations by humans by eye, but the instrumented observations started with Torricelli with barometer and Fahrenheit with, mercury thermometer. And past 4 centuries, there has been so many instruments, but since 1960, entirely new set of instruments for observations are available, right? Which is the satellite. And I'll restrict only to the satellites because the way the satellite look at atmosphere and the way they draw information out of it is entirely different from other in situ observations. So traditionally, meteorologists have observatories, right? They also, since many years, they launch balloons and see the structure of the atmosphere. Now they also have many radars, which from ground look up, and it's also a form of remote sensing, right? But I am interested in satellite-based remote sensing, which we will introduce to you. So as far as the IMD is concerned, basically the observatories at Calcutta and Madras were established in the late 18th century, right? So there were observations available, and then there were also treatises. There were also work done on cyclones, but after a major cyclone in 19th century last quarter, the imperial government decided to establish India Meteorology. So it was established in 1875. First, it was in Calcutta because Calcutta was the seat of the government. Then it expanded nationally, and then the headquarter moved to Shimla, right? Then it expanded. Then at certain time, the all observations were transferred by telegraph, and of course Shimla has a winter, it's not very easy. And then it moved to Pune, and it was called Shimla office. So the headquarter of IMD was in Pune, but it was called Shimla office. And finally, it ended up as many things in Delhi, where it has a magnificent infrastructure and building. And it also then, the surrounding of the building then had established a National Center for Medium Range Weather Forecasting. Dr. Ramesh was there, which had India's supercomputer, and now they have a huge, almost 10 plus petaflop type of a computing facility to do forecasts. This can be the shortest introduction. So as far as the satellites is concerned, the IMD started getting the global data, but the Indian satellite INSAT, Indian National Satellite System, was first launched in 1975. So the INSAT 1 series were all, made and integrated in US, and they didn't really perform very well. So only INSAT 2E onward, when the at ISRO and Space Application Center, the sensors were made, then we have a whole series and continuous observations. I'll come to the from 2000 onwards, the geostationary satellite. But that we have moved ahead. But here, before we move further, it is important to understand what exactly is the remote sensing. So remote sensing is the science and art of obtaining information about an object, area, or phenomena through analysis of data acquired by a device that is not in direct contact with area, object, or phenomena. So this camera is a remote sensing equipment. Our eye is also remote sensing equipment. The difference between our eye and this is our eye, takes the information and puts it in our brain. Some we recall, some we don't recall, and many things we don't have that type of quantification and reanalysis capability, which when you have a digital remote sensing system. But then when you want to go in space, so that called for another technology. That technology started in 1957 by launch of Sputnik by Russia. Sputnik was a small ball, not very big, and it only could, transfer some signals, radio signals. But then what happened? It spurred a race, and then America launched Tyros 1 in 1960 April, and that was a mission which actually imaged the cloud systems, and then the satellite meteorology was born, right? So we would then uh, in between some area we will skip, but for you to understand satellite meteorology you have to understand a couple of things. Since the sensor is not in contact with the object or phenomena, so what transfers the information? This information is transferred from that object or phenomena to the sensor by electromagnetic radiation. Now, electromagnetic radiation is a very, very large span, right? But the one what is used for remote sensing is much limited, right? So, from let us say UV, below UV are very high energy particles. You can use UV and oxygen absorption, then visible, green, near infrared, then far infrared, shortwave infrared, thermal infrared, right? Then you can have the uh, millimeter waves, microwaves for a whole range. Then you go to UHF, etc. So, but across this spectrum, everything cannot be used. If any part is fully absorbed by atmosphere, you can't use it. Right? So if that radiation cannot go through atmosphere, it is not suitable for remote sensing. But even if it is partially used or absorbed, still you can get some signature if you are able to correct for it. So the interaction are of three types, right? Interaction, one is the transmission, the other is scattering. So scattering depends upon the size of the particle. If they are at wavelength level, you have one scattering. If they are larger than the wavelength, you have a different scattering. If they are very large, then you get non-selective scattering. So scattering basically throws that signal in all directions, which creates noise, right? But then what is important is clouds do non-selective scattering and very high albedo, which is then used to identify the cloud. So once we have understood the natural radiation, then the sensors can both be passive and active. So passive sensors are those which either measure reflected solar radiation, right? So you can take your camera, if you take a picture in whatever natural daylight or night condition, it is passive. But if you put on your flash, right? So this light will fall and then reflected thing will get image in your camera. Then it is called active. So now what are the active sensors? Active sensors can be in light range, basically lidars, right? So there very few lidars are in space, but they provide very critical. Most of the active sensing is done by radars. So basically it is radio detection, and you send a radio wave and you get back the signature. Now the interaction of radio wave is totally different from interaction of the light wave. And in the thermal you have passive, which is emission, right? So but microwave, the interaction is more due to structure, dielectric, right? So let us say if you have water, you have a different type of interaction, high dielectric. If it is sand, soil, dry. Third is microwave. When they go in a porous media like a vegetation canopy or a cloud, you get volume scattering, because the reflection back scattering happens in various directions. So the entire volume back scatters, so which creates a different type of signature. So this is the interaction, differential interaction between the objects and the wavelength and the type of sensor is what makes this observation. I will show to you almost a whole range of hundreds of parameters are updated. But that is not all. We only talked of a sensor. Now a sensor will not go into space because it doesn't have an environment. So sensor requires power, it requires a platform, and it requires communication of the data. Right? Now, in space, you can't hang an object. It will simply drop or go somewhere. So these sensors are put on satellites which are on particular orbits. So this is very important. From sensor to satellite, you must have a platform of the satellite and an orbit. Now, designing of an orbit and the imaging characteristic of sensor can give you very, very diverse type of. So for imaging, because if you are doing optical imaging, you want sun to illuminate earth at the same local time. So what you do, you use what is called polar. You use a polar orbit, where polar orbit is from north to south, it moves. The height can be anywhere between 400 to 900 plus. It takes about 90 to 100 minutes to cover one earth. By that time, the earth would have moved west to east, and then it will image again, right? Depending upon the sensor and quality you get. So this polar imaging will then give a strip, and then you will join the strip. I'll show you the power, etc. slightly later. The second important point is you can, all of you can remember your physics, right? So you put the force, right? The gravitational force between two objects, F gmm by r square, right? So then what will happen? G is constant, right? Mass of the earth also, one body is also constant. So you can really get at a stage where at some r, where these two forces of that centripetal and gravitational, they balance, and if you put the satellite there, it will go on revolving around the earth and look at one point. These are called geostationary orbit, and that geostationary position happens at 36,360 odd kilometers, right? So now what happens once you put in the geostationary, you can then image multiple time in a day, and you can image. So the although geostationary is preferred for some meteorological studies, etc., but equally large number of sensors are orbiting also. Then there are two, or let us say three different orbits. Let us talk of India. India is, let us say, between 4° north to 38° north, right? And if we are orbiting, then we don't want to waste that much time on going above that. So what we could do, we could have an inclined orbit, right? And it may go up to 30, 40 and then come back. So what will happen? This time it will take will be much less, and you will in a day cross over India couple of times. I'll show you inclined orbit. There is another way. You can have something as a equatorial, but it should be fully equatorial. It should be near equatorial. So we had a satellite called Megatropics done with Ganesh. So it used to have, between 3 to 5 in one day images. So then short phenomena can be captured. So it is not that you have to very, as a system study, define your parameter and observation and time frequency and decide the orbit. But anytime you decide the orbit, you have to also worry about how to get the data back to you. So there are 3 ways. One is to have a ground station and transmit. The second one is called a TDRS. From that satellite, you send the data to a geostationary satellite and then get it back. Third is you download at poles or a ground station and then use either the geostationary or local network to get the data, because getting the data in time is as important as getting. So this, I think, is one. I think I missed only one point. Since we discussed the atmosphere at height also is important. So how the satellites will do? So there are 2 modes of getting the composition of the atmospheric structure by height, right? From ground, we can put a sensor and a balloon, which will go up, and depending upon the volume and our computation, up to 30-35 kilometer also, it can measure ozone and many things. But for satellite, how to do? So one is to use those channels which will interact with different, pressure levels, or what is called limb sounding. So in limb sounding, what you do is you orbit around the Earth, but you look at the sun. So once what will happen, from outside the atmosphere, you will look at the sun and then you will fall into the shadow of the Earth. Then on the lower side, from the shadow of the Earth, you will emerge and again look at the sun. Since the sunlight is passing through the atmosphere and you are sensing, you will actually get at various heights the information. It can be atmospheric chemistry, it can be atmospheric, particles and various type of things, even atmospheric emissions. So now I think you've understood that it's just a satellite and a sensor, but choice of the wavelength, choice of the imaging mode, choice of the particle, the interaction, it is such a powerful technique. Right? So then you have then many different categories of satellite. You have atmospheric satellite. Weather, atmospheric means atmospheric chemistry and other. You have weather satellite. You have ocean satellite. You have land satellites, including for cryosphere, because the polar ice caps, by reflecting sunlight, modulate the albedo of the Earth and control the weather. So it's a very, very important phenomenon. Plus, don't forget that in addition to imaging, you can have a satellite to be used as a data collection platform. So what happens, suppose I want to get some data from the ocean. I have some float, some sensor in the ocean. So as the satellite will pass, it will compress all the data and send to the satellite. And from the satellite, it will be received on the, right? That is one way. And the second important point is, there are, all of you have mobiles and GPS. You can reach Nias and then you will go home by calling Uber. So the GPS is done by position, navigation, and timing satellite. So the PNT satellite use L1 or L5 frequency. They are MEO. They are in the sense of the 20 to 24,000 kilometer. And then if you receive signal from 3 satellite with very accurate timing, you can do a triangulation and exactly know your location. Right. But the point is, there are sometimes errors. The error is due to the structure, the humidity, and the ionosphere structure of the atmosphere can make the signal to delay. So same way, you can at a fixed point, if you receive and you are getting the variation in the location, you can invert it to what is happening to the atmosphere, water vapor, and ionosphere. So this itself is a remote sensing of the structure. Generally, we do only the lower part of the atmosphere. Above troposphere, it is covered as part of aeronomy, upper atmosphere, right? So now you have understood that satellites, various sensors, various and modes of functioning. So then it gives rise to what would be the application. Cloud imaging, atmospheric chemistry, the ozone and ozone hole you would have, land imaging, albedo of the earth, snow, soil moisture, because the soil moisture changes the partitioning of energy between sensible heat and latent heat, right? So what will happen by this one particular parameter can produce a different location, very, very different weather local conditions. So it is a very, very important meteorological parameter, soil moisture. For ocean, the sea surface temperature, ocean color, right? Uh, the ocean wind, ocean wave, and ocean salinity. And of course, Arctic, Antarctic sea cover and sea ice. So now you have understood this technique totally covers the earth and all the features of the earth with observation. And the good part is, compared to normal observations, which are a point in time or whatever point in space, it in a regular grid covers the entire earth. Two, since you are having a orbiting sensor, so the same sensor is collecting information at different parts of the earth, right? So the sensor biases get reduced, but you get drifts, and between two sensor system you have to calibrate and bring them to common geophysical quantity. So I hope I have tried to explain to you the power, utility, and mode of use of satellites, right? Then I think before we go further, I just, it's a very, very busy picture. You can sort of, you can just Google to this and find out. But why this busy picture is important is, you will see some lines, right? Red, blue, yellow. Each line is touching a very, very specific part for clouds, for ocean, for aerosol, for fire. And then it has a different type of sensor. And some have multiple suites of sensors. And it has lidar, calypso, it has thermal band, it has the meteorology GPM4 on cryosphere. So what it means is you require a large number of satellites. As of now, something like 1,000 plus satellites may be there, but they are all Earth observation. If you even talk of remote sensing, sorry, atmospheric and meteorology, there would be not less than 200 satellites, which are actually used for various applications. So we are not talking of one, we are talking of numbers in 100. Each one is collecting huge data. and then satellites are the biggest source of what is called the big data, right? So some of these satellite annually they do terabytes of data, and in their life they really do uh, petabytes, right? So this roughly explains to you almost every feature, right? Has so which are missing. New and new sensors are being designed. So at this stage, let us come home and look at the website of IMD and look at the geostationary satellite and visible and infrared images, right? So now, since you are geostationary satellite, you can image every half an hour. American system images every 15 minutes or so. On need basis, Indian systems can also do. So you can see India, you can see ocean, and you can see the cloud. The interesting part is you can use 3 consecutive images, right? And find one each point of the cloud, how much it has moved. So you can write automated algorithm, and this is called atmospheric, a cloud motion vector. Now the point is, for this you will have to assign a height to the cloud. Otherwise, you won't know. And as we discussed, meteorology is a atmospheric dynamic phenomena, right? It is you can uh, only by understanding this atmosphere dynamics, and then you can use it. If you have local data, you can use nowcasting. If you take geophysical parameter, you can put them into a numerical weather prediction and make a forecast. And for longer forecast, you need to cover more and more region. For more longer duration forecast, you after atmosphere you need to couple ocean, land, and so on, right? And then if you want to do 50 to decadal to 100 year, you need a Earth system model, which will have the our future type of pathways, what we will have, what will happen to energy, land, human being, and then predict. So the entire those things what you hear, what will happen in 2100 or 2200, are all based on Earth system model. So there is a range of numerical weather prediction model. You can have model at different scale, mesoscale, global, and then you can also have coupled with ocean and more coupling and more parameter, which itself is a very, very vast field. Okay, so but at the heart of it, global observation is the satellite. Without that satellite data, so what the studies have shown is, if you the 50s when it started, from there to now, if you see, if you remember your geography, the northern hemisphere has more land and southern hemisphere has more ocean. Obviously, there are more meteorological observatories in northern hemisphere and less in the southern. So if you want to compute the forecast accuracy, northern hemisphere had better accuracies. Of course, within northern hemisphere, Europe and US had better, and southern had poor. But as the number of satellite, their parameter has increased over last 40 years, the difference between the two has almost vanished, which actually shows the power. It's a very famous picture. You can locate it and take a look at it. That brings us to another. So this picture and getting the data is not the whole story. It is the geophysical and quantitative information extracted, converted into a service or an impact, and then finally communicated to the society. What Dr. Mahapatra was mentioning, was the commitment of the IMD. So you can see the rainfall information, the monsoon information, the agromet advisory services, aviation services. In fact, you may not know, after the First World War, when the aeroplanes started moving, the militaries found meteorology to be very, very critical for their mission and aeroplane flight. In fact, IMD was also part of the civil aviation, and at each airport, you would really have a IMD office, because without that, the aviation will actually be not so safe, right? So then climate services, hazard. So hazard, cyclone information. In fact, cyclone, if you look, till 90s, cyclone used to produce very, very large number of deaths. So over past 20 years, the satellites are able, through numerical weather prediction, tell us the path of the cyclone. I'm sure you must be seeing. Then they are able to predict the intensity at the landfall, location of the landfall, and time of landfall, and then predict the heavy precipitation and wind due to the cyclone and the damage. So all this, when a big cyclone comes, states like Odisha, they shift 2 to 8 lakh people from their home to safer places for 2 to 3 days, right? And then these people come back. So all this is because of the power of the satellite observation. So while IMD is the actual user and analyzer repository, the other Indian government organization is the ISRO. So in ISRO, at Space Application Center, you build sensors and application. Satellites are built at URSC in Bangalore, right? Launching is done in Sriharikota. The satellite control is done at MCF Hassan, right? And making of the launch vehicle happens in Trivandrum. So meteorology and oceanography at the MOSTAC data center. So you can look at the missions. India INSAT is a geostationary, then Kalpana, then you have 3A. Megatropics was with French agency Canis, and it was doing the water and energy cycle of the atmosphere. Saral Altica is an altimeter. Then OceanSat 2 and 3 are for ocean color, and SCATSat 1. Uh, there is a very different concept you will appreciate. In a scatterometer, you send the microwave signature in a forward direction in a scanning mode, right? So what happens when you are over an ocean surface? Ocean surface is rough, so this they will come back depend, and that will be controlled by roughness. So in a sense, this entire global ocean, the ocean wind is a very, very important critical parameter. Huh? And you can globally map the ocean wind, but there is a limit. Totally calm ocean you can't get, and if it is a very rough ocean, obviously you will not be able to. That linearity between the ocean roughness and the backscatter will go. So, but for most of the operational range, you can really do the this. But in OceanSat 3, ocean color, SST, and scatterometer, all the three are put in the OceanSat 3. So I'll just show you the satellite missions. So the missions are on upper is geostationary, and then the Leo orbiting one. So Kalpana was the first meteorological satellite, a standalone. So there is a small history. When ISRO was to be formed, then the PRL, the place where ISRO was born, they thought that for India, communication, teaching the rural people, two, the disaster service, and three, the monsoon. So India was the only first country at that time to configure a satellite which will do imaging also. Earlier at that time, the satellites were either geostationary or rotating satellite for meteorology. But then, because you wanted to put imaging and communication, so it became a asymmetric satellite with a long tail. And when the two failed, people felt that it is a wrong concept. But later on, it was proven it is not to be so. So then it has a AVHRR. They started with 8 kilometer uh, infrared and 4 kilometer visible. Then INSAT 3A, it also had the CCD charge coupled device. Then INSAT 3D, which is launched, if you are able to read, in 2013, it had a sounder. So, but the sounder is not functioning since 2020. So INSAT 3DR was the repeat. And then we now all have the launch of INSAT 3DS, which is the 3D spare part. And then GISAT are the yellow, which is in future. I'll explain to you what it is. In the low Earth orbiting satellite, uh, we have the OceanSat 2, then followed by the Megatropics, Saral Altica, ScatSat 1. Now we have OceanSat 3, what you see in the green color, which has the ocean color, the SST, and also the scatterometer. See, sea surface temperature is one of the most important parameter, important for cyclogenesis, important for many weather phenomena, total evaporation of the water from the ocean, right? But unfortunately, under cloudy conditions, you can't get it. So more so, also what is now being put there will be microwave based missions to do all weather conditions, right? So this is a very short summary of 3 decades of both geostationary and other missions. Okay, so, and this are the uh, channels of the imager: visible, shortwave infrared, middle, water vapor, TIR1 and TIR2. You require 2 thermal channel to correct for the atmospheric water vapor and really get the land surface temperature. And the whole disk, as imaged by INSAT 3DS, is also put here. So it was launched on 17 February this year by GSLV F14, right, from SHAR. It also has a 19-channel sounder, right? The other important satellite what we have is the for ocean, which, as I said, scatterometer provides ocean wind, which is a KU band scatterometer, and it has an ocean color, SST. It also has Argos, where the buoys they go down, they come up, and then all the ocean depth parameters are transmitted, which actually goes to the one common site and gets distributed globally. There are new ways of looking at it, and one of the most recent one has been to have a microwave humidity sounder. Now this is in uh, sort of 183 plus minus 15 gigahertz. So 6 channels are there very close to each other. So this is a millimeter wave or terahertz sounder, because 183 the electronics and the design are. So why do you need multiple sounder? Because at different wavelength, the weighting function, the GMF for that particular band is different. So by integrating all this, you can actually get the vertical structure. Sounding means in atmosphere you don't get total humidity. You also get at various levels what are the, and the change because of the sounding is a very very important information of that. So have I covered my time or uh, 5 more minutes are there? Then quickly I will jump to uh, just two picture and one particular thing. So in ocean, what happens? Many other things are there. This is one very important example at Gulf of Oman, where high algal blooms. You can actually see the radiation which falls on the ocean. If there are no phytoplankton, etc., you get a physical response. If the phytoplankton are there, they absorb some of it. They use it for photosynthesis. Then the like as I was telling you, the radiation balance on Earth by soil moisture, the partitioning between sensible and latent heat. Ocean also heavy the pigment phytoplankton can slightly cool the ocean surface. Okay. The other important point we were looking are the essential climate variables. So of almost 60 plus, more than half can only be done by satellite. So at NRSC, where I used to work for some time, we have lot of parameters which you can go to the Bhuvan site and download, including these are all derived parameters, geophysical products, which has ocean heat content, it has soil moisture, type of vegetation, snow fraction, monthly, weekly, etc. We all know that we are entering into a very, very dangerous uh, era of more CO2 and climate change, right? And plus, we are modifying the various land, etc., which gives to global change, biodiversity loss, and so many other things. The satellite and meteorology, as I said, is critical to understanding it. These are some of the parameter. And if we heat, one of the things that will happen is that the polar ice caps can melt or reduce. There will also be carving of the shelf and big chunks as big, as a country can actually do. I'll just show you one picture. Uh, so one such event happened where very large shelf got broken, right? First a line happened, melting, then thinning, then a crack, and then it moved away. Also, what is happening is during the winter time around poles, you have the sea ice. The extent and seasonality of sea ice is also changing, right? So I will stop here. I think I have tried to explain to you the critical role the satellites play in meteorology understanding, in observation, in forecasting, in doing for disaster like cyclone, drought, etc. And then including how they can monitor trend and future what is happening. So if there are some questions, I will be attempting to answer.
Thank you very much, sir. Ubi, you can coordinate for questions and answers.
Yes, Dr. Soni.
Sir, wonderful and very nice presentation. It conveys to the students and faculty to a great extent. As the saying goes, clouds are obstacle for all astronomical observations. As we look from the surface of the Earth outward, can we expect that the satellite meteorology also have the same kind of riddles while observing from top till bottom?
So what I was explaining to you is the active remote sensing and the passive emissions. They can pass through clouds. So visible NIR, yes, but in NIR, if you look at the cloud, and if there is a convection cloud moves up, the temperature drops very fast. In fact, this signature allows you to do quantitative precipitation. So what many people feel is a noise actually is a signal also for a particular phenomenon. So astronomy, you are fine. That is why we actually go to Leh and Hanley, right, to do put the telescope. But to all the youngsters, I can give you a very, very dire warning. What is now happening? The satellites have become so cheap that anybody can make a satellite into $4 million. And companies, whether US, etc., including Chinese, they say we will launch 20,000, 30,000 satellite constellation. There is a private constellation called Planet. They have more than 350 kg satellite. They can image any part of the Earth every day. 14 million images they collect per day. Now, if you have thousands of satellites, so what has been noticed and also simulated, all telescope, whether Leh or wherever, right? They will actually, whenever the satellite will cross through, there will be a reflection and streaks of light. So which will make billions of dollars of investment on ground-based telescope go waste. Or you will have to sort of filter out, take that period. So this actually is one of the negative side effect of rise of CubeSats and dropping of the cost of the satellite. So astronomy, ground-based telescope astronomy will be one of the casualties.
I think online, sir. Anybody? Online? Sir, no question from this side.
Sir, let us thank Professor Dadwal for kindly sparing the time today with us. And now I would request Dr. KJ Ramesh to kindly deliver the lecture. Over to you, sir.
Thank you, Sony, and other colleagues, online colleagues joined, Dr. Mohammed, and asking me to speak on this 150-year foundation celebrations of India Meteorological Department. As you all know, that climate is changing and global warming is there, that everybody is experiencing the adverse impacts of climate change. So in these particular aspects, so several general articles have come and scientific assessments are done by United Nations Framework Convention on Climate Change, and IPCC generates scientific assessments of climate change and generates all scientific inputs to United Nations Framework Convention on Climate Change. So every year, UNFCCC meets, that is Conference of Parties. So currently, one Conference of Parties is going on now, and we will have some policy decisions taken by all the governments.